Hi guys, we're going to talk about relations and functions today. This is the first section in the chapter 2, and it's kind of a loaded section, so I hope you take some good notes and really pay attention and ask questions if you have them. So let's start with this warm-up. So this is a really big idea in math, and it's called multiple representations. They really push math teachers to work on this with our students. And this is so important because there are 4 different ways we can write relationships in math. So what are they? Well, the first one is an equation. That's the first multiple representation. And it looks like this. And you could also use words. Kids don't use words very much. It would say that y is the value of x squared minus 1, or 1 less than x squared. That would also be nice. We can graph it. We can make a graph. That's another way we can represent this picture. In the way we make the graph, if you remember what a parabola is, it's x squared, and this would be a downshift of 1. And we will learn more about quadratics later this year. You could also make an XYT table. You can make the XYT table first and then graph it. That might have been helpful. So if you're at 0, 0 squared minus 1 is negative 1. 1 squared minus 1 is 0. Negative 1 squared minus 1 is 0. 1 squared is 2 squared is 4. 4 minus 1 is 3. Negative 2 squared is 4. 4 minus 1 is 3. So you could graph. You could write it out as ordered pairs. Negative 2, 3. Negative 1, 0. 0, negative 1, and so on. These are all ways that you can write it out. And I said there are 4. The 4 big ones are graph, equation, table. Oh, maybe it's words. Maybe it's words, this last one. I don't know. But it's kind of like 5 when you consider the ordered pairs. So when you have ordered pairs, this is called a relation. Any set of ordered pairs. My favorite types of relations are the ones we did in middle school, where your teacher would give you all these ordered pairs, and you would graph them, and you would connect the dots, and it would be something like Snoopy when you were done, or a pumpkin, and you would color it, and you'd hang it on the wall, and it was really nice. Any set of ordered pairs, they're not really related anyway, they just made a pretty picture. And that's a relation. And what domain is it is the first elements. Usually we think of it as the x values. In the range are the y elements. And an easy way you can remember that is range is y, because if Mrs. Bruno started randomly singing in class, hum, hum on the range, and the kids are walking by, they would say, why is she singing? Why are those poor kids in there? Why is their teacher so strange? When she sings Home on the Range, she's talking about why. But it doesn't just have to be X and Y. It can be any set of ordered pairs. For example, we have states and capitals. If I write down the state, comma, the capital, could have picked a longer state here in the capital. It's not X and Y, it's the domain would be states here. Oops, and the range would be capitals. So it's basically whatever you're talking about. A lot of times it's X and Y, but it's really just the first set and the second set. Sometimes we call the domain the input and the range the output. That also works. Sometimes we call domain independent variable, because you get to pick. And sometimes we call the range the dependent variable. These are all different words for what means the same thing, domain and range, what X is allowed to be and what Y is allowed to be. So here are, there's the 4. There is 5, so I don't know why I wrote 4 earlier. You have equation, words, graph, table, and ordered pairs. So where does the domain and range show up in each of these? Well, equations, it's kind of tricky. It's basically what are you allowed to plug in for X. It's way easier to find domain in graph, table, and ordered pairs. The domain in the table are just those X values. You cannot assume There's more values to a table unless you have an equation as well. And we do here. So you could plug in 0.5 if you wanted, but if you just have a table alone, you have to assume that's all there is. A graph, where does the domain shows up? It shows up in all the values, left to right. In the picture, can you go left forever and can you go right forever? And the answer here is yes. So the domain is actually negative infinity to positive infinity for this graph. For ordered pairs, a lot of times we will say the domain like this: the set of all x such that x equals, and you can list out what you have here for x. Okay, now for the range, again, it's trickier in the equation and words, but for the range, you're looking for the y values in these multiple representations. So in the graph, that's talking about the down and up. So this graph bottoms out here at -1. So it starts at -1, but it goes up to infinity. So the range values would be -1 to infinity. The range values could also show up in your table, and you could just list those out. The same with the ordered pair. You could say the set of all y such that y equals 0, -1. I don't have to list 0 again. 3, ... Okay, so you can connect the dots if you have an equation and you know what's going on. If you just had a table or you just had ordered pairs and no equation, you can't assume that the dots are connected. So just be a little bit careful with that, but we will have lots of practice. So here are some more domain and range examples. This is called mapping notation, and this is our ordered pairs. Basically, this is saying the same thing. This mapping is a way to write your ordered pairs. They just put all the x values here, -3. -3 is there again, -1. So what would B be? B would be 1 here. And then the x values show up. Excuse me, the y values show up. -2, 0, 2, and 2. So A would be 0 here. These lines represent the mapping that happens. It takes the x value of -3 to -2. The x value of -3 also goes to 0. The x value of -1 goes to 2, and the x value of 1 goes to 2. So this is mapping notation. The domain would show up here. The range would show up here. In the ordered pairs, the domain would be the x values, and the range would be the y. Okay, you can use inequalities to describe domain and range, or interval notation. So let's talk about domain here. What is x allowed to be? That's your left to your right. Well, if you go all the way to the left, it looks like your graph is starting right here at -4. Interval notation is a little easier for me. I'm going to do a parenthesis for -4 because it cannot equal -4 because of the open circle. It goes to the right all the way over to 4. It can equal 4, so that's a square bracket. That is interval notation. You could also say the set of all x such that you can put the small number less than x less than equal to 4. Forehead, nose, and chin. That's another way to write the domain. For the range, you're talking about the down, up, the small to the big. So where does this guy bottom out? Looks like the lowest we get here is at -2. Can be -2, so that's a square bracket. And it goes all the way up to 5, but the 5 gets the open parenthesis because there is an open circle there. You also could say the set of all y such that, small number first, -2. This time that gets the less than equal to y less than 5 because range has to do with y. Two ways to represent domain and range. Okay, next thing, this is the big guy, functions. I went almost my whole high school career not clearly understanding functions, and it made my college life a little bit more difficult. So I think you really should invest some time in trying to understand what these functions are. And basically, they're just special relations. They're definitely going to be ordered pairs, equations, tables, and that stuff. But these guys are special because of this. Each x only has one y. So when we were talking about our coloring the picture and making like a pumpkin out of those dots that you used to do maybe, I don't know if this is going to look like a pumpkin or not. Maybe. Yeah. And then like these are just random ordered pairs that I made the pumpkin with. But if each x only has one y, I call it a predictable machine. So what do I mean by a predictable machine? Well, all my machines will always look like this. We'll draw a lot of these this year. And let's talk about this function that I'm going to tell you, and it's y equals x plus 1. Okay, x plus 1 is a function. I'll tell you why. Because basically the function machine is a rule. It does something to things. So we're going to plug in values into this funnel, and it's going to be, this stuff will be done to it, and it will shoot something out. So if I plug 2 into my machine, it's going to shoot out 3. If I plug in 4 into the machine, it's going to shoot out 4 plus 1, which is 5. If I plug 9 into the machine, it will plug in 9 plus 1 and get 10. I can plug whatever I want into this machine. This machine, nothing breaks the domain of this, which we'll talk about in a minute. But let's say, I'm trying to get pink. Come on, pen, where you at? Let's try again. Sorry, I know you really wanted pink. -7. -7 plus 1 is -6. Now, for this machine, let's say later somebody comes in the room and they say, hey, I want to plug 2 in. This machine always, always, always turns 2s into 3s. That's what it means by each x only has one y. Every time somebody plugs a 2 in, it shoots out a 3. There never becomes a time where somebody will come in and plug a 2 and maybe it shoots out a 10. That's not predictable anymore. The machine is doing some things to these numbers and turning these numbers into other numbers. So this is a function. Now, this is an example of not a function. And the reason it's not a function is because when I plug in -6, it shoots out 1. So far, so good, not a problem. But look what happens when you plug in -3. If Mrs. Bruno plugs in -3, it's shot out a -2. Then Mrs. Thurston comes along and she plugs in the -3 and it shoots out a 4. This x has 2 different y's, so it's not a function. This guy is a function. Each x has only one y. Now, what's happening here? Well, it's okay. For this particular function, when you plug in 1, it shot out a 1. If you plug in a 2, it's also shooting out a 1. But that x only has one y. It doesn't have 2 y's. So later, if Mrs. Thurston comes in and plug a 2, it's still going to shoot out a 1. If Mrs. Bruno plugs in a 2, it's going to shoot out a 1. So that's okay. In fact, one machine that kids kind of get confused on is this function machine, y equals 4. And this machine just shoots out 4 all the time. That's all it does is turn everything into 4s. So if you plug a 2 in, it turns into a 4. If you plug a 3 in, it turns into a 4. A 7 in, it turns into a 4. It is a function because each of these x's only has one y. They're all the same y, but that's okay. Now, this guy here is a special function. He's definitely a function. This one is what we call a one-to-one function. A one-to-one function means each x has a y and each y has one x. So there's a match this way. If you plug in a 2, you get a 5. Nobody else can get a 5. Only the 2 can get a 5. So that's what makes it one-to-one. We're going to talk a little bit more about these functions throughout this lesson. So how can you tell if a relation is a function or not? Well, the easiest thing to do is just to check the x's. All you do is check the x's. If any x repeated, it has to be predictable. It has to be a duplicate. So let's go back to this first guy up here. I check the x's. None of these x's repeat. So it has to be a function. There's no duplicates. When I go to, let's see if I can find another set of ordered pairs that we looked at. This one, here's a -3 in the x spot, and it shot out a -2. But here's a -3 in the x spot, and it shot out a 0. So I checked the x's for repeats, but the -3 did not duplicate. It's no longer predictable. That was not a function. So if there's no repeats, you're good. And if it does repeat, as long as it's a predictable duplicate, you're fine. Now, what if you have a graph? Think about that graph, y equals x squared minus 1. Looked like this. I can't check all the x's. It would take me my whole entire life because there are infinitely many points to check. So because a graph is actually a picture of all the solutions, what we can do is this idea called a vertical line test. And a vertical line test is a way to visually check all the x's very quickly. Because if negative, I'm going to erase all my lines I made here. If I plug in -4, let's say it's up here, you can tell it's only shooting out one value because it would be right here. If I plug in 1, it's plugging in this guy. If the graph looked like this, it would not be a function because when x equals 0 here, sometimes the graph is shooting out a 2 and sometimes it's shooting out a -2. So this is not a function and this is a function. So it passes the vertical line test and every vertical line only touches once. That means each x has one y. If it touches more than once, it fails the vertical line test and it's not a function. So what about a one-to-one? How can you tell if a graph is a one-to-one function? Well, each x has a unique y, which means it has to pass the vertical line test, but each y also has to have one x, so it would also have to pass a horizontal line test. So when you look at the parabola, this is a function, yes, each x has one y, but is not one-to-one because it fails the horizontal line test. Because the y value, we'll go back to our table that we had over here. The y value of 0 shows up twice with different x's. So it's a function because each x has one y, but it's not one-to-one because there's a couple y's that have the same x. Okay, so let's do some practice. Are these functions or not? If they are a function, are they one-to-one? So let's look at this guy first. Is it a function? Well, let's check the x's. The -3 goes here, the 5 goes here, the 3 goes here, and the -5 goes here. Each x is only going to one y. This is a function. So that's a yes, function. Is it one-to-one? Well, this 6 is going both to the 5 and the -3, so it's not one-to-one. It's just a function. There's not a lot of room here. Okay, so let's look at this table here. Let's check the x's. Do any repeat? Oh, yep, here, these two repeat. So now we check. That one goes with a 2. This one goes with a -2. So that means it's not a function. If it's not a function, it's definitely not a one-to-one function. So it's not a function. Okay, how about this graph? Is it a function? Pass the vertical line test? No. At this value here, guys, at -1, it shoots out 1, 2, 3 different variables. So your machine's not predictable. That's not a function. Our parabola is a function. Each x only has one y, so that is a function. Is it one-to-one? No, we already talked about it. These y values have two x's, so it's not one-to-one. Here is some ordered pairs. Let's check the x's. 1, 2, 3, 4, 5. So it is a function. No repeats. Is it one-to-one? 3, 5, -4, -3, -1. No repeats there either, so it is one-to-one. So that's how you check if something is a function or one-to-one. So real quick reminder, relations are any ordered pairs. Functions, where each input has just the one output, it's kind of predictable. And one-to-one is each input has one output and each output only has one input. Next, we're going to talk about function notation. This is how a lot of us write equations. And when I was first taught functions, I was taught f of x is just the same thing as y. And that's kind of true. But you can use function notation for lots of other things instead of just graphing if you needed to. So when you have f of x, what does this mean? F is the name of the function. We're not very creative. It's like the name of the machine. So that way, if you're dealing with two different rules, maybe one you called f of x and one of them you call g of x, you'll know which one you're talking about. X is what we call the input. That's what you are plugging in to the function. So if this is my function f, I'm plugging x into it. And then something happens, and what does it shoot out? It shoots out whatever happens to x after f does it. So f of x is what it shoots out, but most of us like to think that outputs are y, because when you graph x, y, but you can also think of it as x, f of x. So for our function here, f is called x squared minus 1. That means the function's name is f, and this is what it's doing. It's taking something, squaring it, minus 1. If I plug in -2, I can write it like this, f of -2. That means go to the function. Wherever you see the x, take it out, plug in the -2 in parentheses, and figure out what it will shoot out of this machine. -2 times -2 is 4. 4 minus 1 is 3. So f of -2 equals 3. The parentheses are very important because your graphing calculator gets a little bit confused. If you just type -2 squared into your graphing calculator, it's going to tell you -4 because it's just squaring the 2 and then putting a negative in front. You have to put -2 squared in parentheses. This does not mean f times -2. If there's an f or a g or anything like that, it's function notation. It says f of -2, and it means plug -2 into function f. Okay, so let's think about this guy. F of x is 10 minus x to the third. What is the input or the independent variable? What are we plugging into the machine? It's whatever's in the parentheses. That is x. What is the output? That's what the whole machine is shooting out, and that's going to be f of x. Or actually, in this case, it's going to be 10 minus x cubed. That's what it's going to shoot out whenever you plug it in. If you have f of 2, that's telling you to go to the machine, take out the x, put in the 2, in parentheses, 10 minus 2 to the third, and the parentheses weren't really necessary here, but it's good practice. 10 minus 8 is 2, so f of 2 equals 2, and that means when x equals 2, f of x equals 2, and the point 2, 2 would be on your graph. You can use function notation to help you with word problems, and I think this will be the last thing we talk about today. Tickets to a play cost $15 each, and we're going to write a function for the cost of x tickets. So what am I going to be plugging in? I'm going to be plugging in tickets. I'm going to be plugging in x. then that will be the number of tickets that I want to buy. The output, what's it going to shoot out? Well, we're going to call that f of x, or you could call it c of x if you wanted the cost of the tickets. If you want, c would be a good name. And what is the relationship? What am I going to do? I'm going to take the number of tickets and I'm going to multiply it by 15. So my equation will be c of x. I'm going to plug in the number of tickets and I'm going to take it and I'm going to take it times 15. So let's write 15x. What would the domain here be? And be careful when they say domain. What kinds of numbers can I plug in for x? Well, if you graph y equals 15x, that's just a line. But we're not really talking about the graph here. We're talking about things in words. And we're talking about tickets in particular. So what kind of numbers can I plug in? Well, I can plug in whole numbers, actually. So I would say, what is the domain? I would say that it's whole numbers here. Your 0, 1, 2. Some of you might say it has to be the natural numbers. Some of you might say you can't have 0 tickets or you don't have a show. That's fine. I'm okay with that. But I don't want half numbers and I don't want integers or all real numbers because you can't have a half of a ticket. Let's look at this guy. A website charges $3 for each movie you download. They also charge a one-time sign-up fee. So they have an initial condition here. $3 per movie. That's a rate of change. That's going to be like a slope. So what equation will model C of M where M is movies? So what is the cost? We're going to take that initial condition, $14.99, and we'll add to it 3 times each movie. What would the domain be here? Very similar to the last one. I would say either whole numbers or natural numbers. Some of you might say you can't have infinitely many, so you might even cap it out, like as many as there are movies on the website, but that's just doing a little bit extra. Okay, so this little introduction to functions, there's a lot of big ideas here that we're going to talk about a lot this chapter.